Okay. Hello. I think we're ready. Um, do you hear me? Do you see the desktop? Does everything seem okay?
Yes, I see everything.
Okay, great. Thanks. Okay. All right. Missing people today. Okay. All right. So, first, remember, there's a programming assignment out there, the one with the static analyzer. So I thought at the beginning, I'd ask if anybody had any question about the static analyzer. So anything come up, anything funny, anything you wanted to ask about the static analyzer first?
I had a question kind of with the analyzing the apply part.
Uh-huh.
Guess I'm kind of stuck figuring out trying to like access that fun value or that function value and then using it in the apply. But I feel like that's more of a kind of homework type question without trying to give it up. But
Let me see. Okay, so so you're talking about the analyze apply. Or analyze, let's see, which one? Fun or apply?
the apply.
Let's see. Now, okay. The thing about the analyzer is the analyzer does things in a different order than what the evaluator does them in. So, for example, the evaluator will look inside of a function when you call the function. Okay, but the analyzer will look inside of a function when you define the function. Okay, so there's a real so the analyze fun in the analyzer looks more like analyze apply in the evaluator. Now, the analyzer, when you get to apply, the only thing it needs to do is make sure there's the right number of arguments.
Yeah.
Because it doesn't actually do the function call. So it'll just make sure that there's the right number of arguments. And yeah, so now the fun, let's see, when you analyze a fun, you got to make sure that these variables are legitimate. So like you wouldn't have a number here or you know, and the other thing is you can't have duplicate you can't have like in the examples you can't have there. See, that's a mistake. Lambda XX. You can't have the same variable repeated. And see, like this is no, yeah, you can't have the same variable repeated. That wouldn't make any sense. Okay. All right. So when you analyze a fun, you check that the variables are okay, and then you put each variable in an environment so that you can evaluate the lambda part, making sure that it doesn't use any variables that aren't legitimate. Let's see, is that right? Yeah. Yeah. You have to you need to know if the lambda is making use of any undefined variables. Okay. So what variables can lambda use? It can use these variables and the global variables. Remember, in this language, a function can refer to its parameters and to global variables. So analyze fun creates an environment that's connected to the global environment, and it puts these variables in that local environment. then it evaluates the lambda using that local environment. That lets the lambda check for, it's using the variables and whatever global variables there are. Okay, so that's what analyze fun does. Is that what you're doing? It should do, it should check the variables and put them in a local environment, and then check the lambda using that local environment.
Yeah. And then with, like I said, like with the apply, so like for the apply
No, wait a minute.
part,
No, wait a minute. I described that wrong. This variable is the name of the function.
oh yeah,
Yeah. So analyze fun just takes that variable and makes sure it's a legitimate variable and puts it in the environment. Then it analyzes the lambda. Then analyze lambda takes these variables and puts them in the local environment, and then analyzes the expression. Yeah, I was mixing up. Yeah, when you analyze fun has to analyze the lambda. It's the lambda that puts the variables in the environment, then checks the body of the lambda to make sure it's using only those variables and the global variables. So analyze fun calls analyze lambda. Okay. And
okay.
then the apply doesn't really do anything. Apply just makes sure that you have the right number of arguments when you apply a function to here. And then apply only works if this guy is a global variable name. So the only thing that apply can check is if this thing is a global variable name. If it's anything but a global variable name, then apply can't even begin to figure out what function is being called here, because it's not at runtime. So if this is a global variable name, apply can look it up in the global environment. If it's anything else, apply doesn't know what it's referring to. So apply only checks if this is a global variable name, then it can match the arguments to the number of things here. It can check that there's enough arguments here for the parameters here. That's only if this is a global name.
And okay, yeah, and my problem is I'm kind of having issues with that first expression. So that's when like apply. So say that, yeah, that first expression is the function, and then like trying to get that functions like I'm sorry, how can I say like the information pretty much from is what I guess I'm struggling with.
You can't okay, remember, only if this guy is a variable name that's in the global environment can you analyze this.
Yeah.
Okay, so you look at that expression and it should be degree 0. If it's anything but degree 0, then it's more complicated than a variable name. If it's degree 0, then you check that it's a variable name that's stored in the environment. If it's a variable name stored in the global environment, not even any other environment, it has to be a name in the global environment. That's why in the environment, you can distinguish between, see, in the environment, you have to be able to figure out if a variable name is defined globally or not. Okay, so here, defined local tells you if something is defined locally, and then, where is it? Defined global lets you know if something is defined globally or not. So if there's a variable name and it's defined anywhere but the global environment, you can't analyze it. It has to be defined globally. So when you analyze apply, this thing has to be just a single variable name. It can't really be an expression. It's got to be a variable. It's got to be a variable. It's got to be a variable that's defined global. So then it was something defined using the fund. Okay. Then you could look inside of the global environment and get its, then you can look inside the global environment and find out how many parameters it has and can match that up with how many arguments there are here. Okay. If this is a more complicated expression, unless you run the interpreter, you don't know what function this is calling. Okay, so I gave examples in the web page. I gave some simple examples of like that. Yeah, see, here's a global name, but then it's redefined here locally. So when you call this, that does not mean you're calling this guy. Here, you're actually calling G, but there's no way for the analyzer to know that. See here, what this 3 lines of code did here is swap the names F and G. So now F is naming this function and G is naming this function. Okay, but the analyzer is not supposed to figure that out. The analyzer, when it sees this, it says F is a name that's defined locally, so it doesn't try to analyze it. And G is a name defined locally, so it doesn't try to analyze it. Okay. It only tries to analyze like here. H, well, even H here, it can't analyze this because H is defined locally. But here, F is defined there, so it can analyze that. Because this F really is this global variable here. Okay, so when you call apply, there has to be a variable name there. Now, in the language, you don't have to have a variable name there, but if there's anything but a variable there, then the analyzer can't analyze it. Okay. If there is a variable name there, then it has to figure out whether it's been defined globally or not. Okay. You have to make sure that it's not a local variable. You have to distinguish between defined local and defined global. Okay. So like that name is a local variable, so you can't analyze it. Okay. That name is a global variable. Now be careful because see that name is a global variable, but it was redefined locally. So that means you can't analyze this. So you have to do the checking in steps. If that variable is defined local, forget it. You can't analyze it. Okay. If that variable is defined locally, forget it. You can't analyze it. Okay. Okay. So you have to have a variable that's defined only globally. So like this is not defined. This is defined locally, but it's also, but see here, we're only in the global scope. There is no local scope. So in this example, defined locally is defined globally. Okay. But that's what you have to do. You have to distinguish between locally defined and globally defined. So you only analyze things that where, that's what makes the analyze apply a little bit tricky. Analyze apply has to figure out, first of all, is that a variable name? If it's not a variable name, you forget. You just don't do any analysis. If it is a variable name, then you have to distinguish between the local variables and the global variables. It's got to be a globally defined function name. It has to be like, in this example here, it's got to be a globally defined function name. It can't even be a globally defined function name like that, because that variable is really that one there. See, that F is really that F. So it's not that F up there. And this G is really that G, not that G up there. Okay. So does that help?
Yeah, and then yeah, like I said, so once like I check that is globally defined, and then I guess trying to figure out how to compare to see if that function that I'm applying, trying to get the number of arguments, I guess.
Oh, that's just the degree of the tree. That's
yeah. Also,
that's just the degree of these branches. They have to agree with the number of branches here. Yeah. The number of branches here has to be equal to the number of branches here. That's just a simple comparison. If you know, once you found the right lambda expression, once you figured out this name is naming which lambda expression it's naming, then you just compare the number of branches here to the number of branches here. That's all you do. If they have the same number of branches, it's fine. Yeah. You don't have to analyze the branches in any way. You just have to know that the degree of this is equal to the degree of this. Okay?
Okay.
And that's pretty straightforward. Yeah. In fact, the degree of this lambda is just the number of variables here plus 1. The degree of this apply is the number of arguments here plus 1. So actually, all you have to do is compare the degree of apply to the degree of the lambda. They should be the same. Because lambda has variables and then an expression. Apply has an expression, then arguments. So there's the same number of branches here as there are here. So you don't even have to count the number of variables. The number of variables is 1 less than the number of branches of the lambda. The number of arguments is 1 less than the number of branches of the apply.
Okay.
So if this
Okay.
apply is referring to this lambda, you just compare the degree of the apply to the degree of the lambda. They should be equal.
Okay.
Because it's just, yeah, they're in different places. This is variables, then body. This is function name, then arguments, but they end up having the same, there's the same number of branches here as there are here. There should be the same number of branches. So you just compare the degree of these two trees. You compare the degree of this lambda tree to the degree of this apply tree, and they should be the same. The hard part's finding that lambda tree. When you analyze apply, the hard part is getting to that lambda.
Yeah, that's what I'm kind of on right now. Yeah.
You have to, that's a name, and you have to look that name up in an environment to get a pointer to the lambda. So you have to store these lambdas, these functions in the global environment. So you have to store these guys in the global environment so that when you get a reference to them, they're in the global environment. So that's where the analyzer acts like the interpreter. The analyzer needs to store these functions in the global environment so that analyze apply can get at them.
Okay.
Like there puts things in the global environment, but like if you do there, it doesn't really matter. You need to stick the variable name in the environment, but it doesn't matter what you associate to it. Like in the description, I told you just put the value false. Just make all your variables have the value false. But you can't do that for the funds. The funds really do need to point at their lambdas, just like in the interpreter, so that you can find out how many variables are in the lambda.
Mm-hmm.
So analyze fun will act a lot like evaluate fun. It'll put the function in the global environment.
Okay.
Everything the analyzer does is something that the evaluator does, but possibly in a different place.
Yeah.
That's one of the tricky things, is that the analyzer might do the same thing that the evaluator does, but the analyzer, and it's always the difference is in these guys. Okay, almost everything down. Well, these two and apply. Fun, lambda, and apply are the hard ones. Everything else is pretty much straightforward in the analyzer.
Okay? Yeah.
So it's a matter of fun, lambda, and apply. And bottom line is the analyzer's fun is like the evaluator's apply. More or less, the analyzer's fun is like the evaluator's apply, and the analyzer's apply doesn't do very much. Okay? So most of the work in the analyzer is in fun, and most of the work in the evaluator is in apply. So they kind of flipped it. They flipped those two roles.
Okay.
And I think there's enough tests in here for you to figure out if you're doing the right thing or not. I tried to put a lot of tests in here so that you'd get a warning if you weren't doing something quite right. You know,
Yeah.
try to make sure there's enough tests to catch the usual kind of errors. So like this is checking for the same variable name twice. Um, oh, checking this. I made that a separate little program. That's in the assignment. It's over here.
Okay.
There's those examples. The examples from the web page. I think I kind of buried them. The examples from the web page. This example here and this test case here. They're actually over here under the demo program. They're with the demo program. Okay. So you can run them on the demo program, and then you can also put, check them on your version. So there's where there's those test cases. In fact, I put a third one in here that's not in the web page that does a little bit more elaborate a check. So this one and this one are from the web page, and then this one's a little bit trickier still. Does another test. Okay. So those tests test whether you're handling the function names properly. Okay. Those aren't in the semantic error checker. I don't think they are. Oh, maybe they are. There's this one. That might be this one here. Yeah, that's this one here does that, is one of them. See, this F here is not this F here. The function you're applying is not this global function, because the function you're applying, see, it's declared right there. It's a local variable. So that's one of the ones you can't analyze. Okay, because so that's an example. I think that's probably this example here.
Okay.
Long, in one line. I think that's the same example, but like you can't analyze that because it's really this variable here, and it could be assigned to any function. Yeah, because even this G, you don't know what G is. Yeah, so F could be G, and G could be H, and H could be K, and then you don't know how many indirections there are before you actually get to the function. So just because you have a variable name here doesn't mean it's that function, because it could just have a long chain of F is G, and G is H, and H is K, and K is L, and L is M, and M is O, and then O is a function. Okay? One interesting thing is, how does Java deal with this? If you can keep renaming functions, how does Java compiler know how many parameters a function takes? That's kind of an interesting question. In Java, you do something like, you call a function just by saying, you just write f of 3, 4, 5. Okay, so you just, maybe you have you have some object x and you call f on it. Okay, or it could be a static function. So you have but you can give these, you could be renaming functions. You don't have to that doesn't have to be the original name of the function. You can even in a language like Java and C, you can say H equals F and G equals H and K equals G, and then you call K. How does the compiler know if that's the right number of parameters? It does not go through, well, K is G and G is H and H is F, and then it goes looks for F. The compiler will not do that. Does anybody know what it does? How does the compiler, if you did this in C, think about it. If you did this in C, it's a good question. How does the C compiler, the C compiler definitely knows if that function should take 3 arguments or not. The C compiler will know, but it does not go back and it does not trace through here, because it could be even worse than this. You could have the following.
What's that?
If,
Efficiency?
pardon me? Oh. If Boolean K equals Bob, else K equal Alice. You could just randomly assign things. You could just have some random thing here. Depending on whether this thing is true or false, you could either K is Bob or K is Alice. The compiler will know the compiler will know whether that's the right number of arguments or not. How does it do it? It can't even know what function's being called here, because the function was assigned randomly. The name K is being assigned randomly to a function name. But yet the compiler will know that there's the right number of arguments there. How does a C compiler or a C++ compiler or a Java compiler solve that? Any guesses? Any guess? There's something missing in this code. Here, I assigned H is equal to F. What do you have to ask in Java code and C and C++ code? What has to be true when you do this?
They have to be the same type.
Yes, that's the key idea. They have to be the same type. Okay. So this is a function. So that means that H has to have the same type as that function. So suppose that function was an int f taking an int x, a double y, and a int z. Okay, so the function has type int double int returning an int. See, so the function has a type. So the type of f is, well, it's int double int. That's more or less how C treats types of functions. You think of it as like this. It's returning an int, and it takes in an int, a double, and an int. So that's the type. Roughly, that's the type of f. Okay? Now down here, to assign f to h, you have to declare h. What kind of variable is h? It has to be that kind of variable. So down here, essentially, h is, now I'm going to use a weird notation. This isn't the notation that C uses, but essentially you have to declare h to be that kind of a variable. H is a function that returns an int and takes in an int, a double, and an int. So then you can assign f to h. But now if you're going to assign h to g, g has to be the same type. Then if you're going to assign g to k, k has to be the same type. So all along, these variable names, the compiler is keeping track of what kind of function they are. Okay? All right. Now here, same thing with Bob and Alice. Bob and Alice have to have the same type. Okay. So then when it gets down here, the compiler knows what type K has, because all along, every time you assigned a function to a variable, the variable name had to have the same type as the function. So once you assign f to h, the compiler doesn't care that where h got its value from. The compiler just says h takes in 3 parameters. Then when you assign h to g, the compiler says, oh, g takes in 3 parameters. Then when you assign g to k, the compiler says k takes in 3 parameters. So when it gets down here to calling k, it knows that it takes 3 parameters. Okay. So every name in C, C++, and Java has a type, and the function types keep track of parameter lists. Okay. Now, why can't we do that in our language? Why is it down here that we can't check this?
Because it's got a local reference.
Yeah, but so did this.
Well, yeah, but that's not our language.
Yeah, but what's missing from our language? Why is our language stopped from analyzing G? What's missing?
The type check? I don't know.
Well, yeah, we don't know the types of any of our variables. Our variables don't carry type information. The value, so here, f has a value that's a lambda, but the name f doesn't tell you what type it has. You have to look at what's currently assigned to it. So okay, f has type lambda, right? What's the type of f?
In that case, it's Boolean.
Well, be careful. F, the value of f is a Boolean. So see, in a sense, you're right. But what the thing is that the variable itself has no type. You have to look at the current value associated to it to say, oh, its value has type Boolean. But the variable doesn't have a type. This is how Python and JavaScript work. The variables don't have types. You have to look at what value they currently have. So here, f was a function because at that point in time, its value is a lambda expression. Okay? But when you get here, all of a sudden, f gets a different value. And you could say, oh, the type of f changed. The really better answer is that f never had a type. Its value changed, and its value had a different type. Okay, so people even in the Python world, they'll say, "Oh, now f has type Boolean," which is not really a good way to put it. Yeah, it's really not very good to say f is a Boolean here and f is an int here. Well, f doesn't have a type. F has a Boolean value here, and f has an int value here. When you get down here, the only way to know if this function call works or not, is to know what you have to run the program to find out what value f is holding at that point. Like right now, f would be holding 22. And this would be an illegal function call because f is holding 22. If I delete that line, this is still an illegal function call because when I get to that point of code, the value of f is false, which is an illegal function. But if I get rid of that line of code, then this is a legal function call. But what function it's actually calling is this function here of 2 parameters. Yeah. But you only know that at runtime because you have to keep track of the value of f. There is no type information. On the other hand, here, the compiler doesn't have a clue what function you're calling there. It actually doesn't know because the function was determined randomly. See, and you could write this in C. This is actually a clever little trick to write in C. You're calling a randomly chosen function. You flip a coin, and then you let K be Bob or you let K be Alice. But since everything has a type, Bob and Alice have to be the same kind of function. They got to be functions with the same type. So down here, it doesn't matter if you're really calling Bob or if you're really calling Alice, the type of them is going to be the same. The compiler has no clue what function you're calling there. It doesn't really care, but it cares about what type of function you're calling. And the compiler keeps track of that because you're forced to declare the types of all your variables. So the compiler always knows the type. Notice the big difference. The compiler knows the type of every variable, never knows what its value is. In our language, the interpreter knows the interpreter doesn't know the type of the function, but it always knows what value it has. But that's at runtime. See, in the interpreter in this language, no variable has a type, but every variable has a value. So at runtime, when I hit here, I can say, oh, what's the value of f? Is it the right kind of value? Is it a lambda of 2 variables? Fine. Is it a Boolean? Not fine. If the value of f is a Boolean, I have to crash the program because I can't make the function call. So an interpreter the interpreter doesn't know the types of any variable, but it can always look up its current value. The compiler, on the other hand, doesn't run the program. It never knows what the value of anything is, but it knows what the type of everything always is. It keeps track of the types, doesn't keep track of the values. Okay. In a language like JavaScript and Python, where the variables don't have types, there's a limit to what you can figure out until you run the program. You have no idea if that's a legitimate function call until you execute it. Okay, because I could do the same thing up here. I could do what I did here. I could assign the function randomly. I could do something here where I assigned see, there's a random in our language. That's what it would look like. If some random Boolean value, if it's true, set K to be Bob. If it's false, set K to be Alice. Now, in this language, Bob could be a Boolean and Alice could be a function. So then this will work. This will work if you set it to, like this could be, Bob could be a Boolean and Alice could be a function of 2 variables, and then this would work if this was false. But if this was true, Bob would be a Boolean and this would crash. That's what Python programs do. Python programs crash pretty often because there'll be some weird bug in the program where every once in a while you call a function and something's gone wrong and the value of the function is inappropriate. There's some bug in the code and you end up with an inappropriate value for that variable. That can never happen in a C program. A C program can never have an inappropriate value for K. It might crash for other reasons, but it can't crash because there's an inappropriate value in K. The compiler is always keeping track of the types of the variables. You can't assign Bob to K if Bob doesn't have the right type. And you can't assign Alice to K if Alice doesn't have the right type. If it's got the right type, then you're guaranteed that that function call is legitimate. Okay, so you never have an inappropriate value in a variable in a compiled language, in a language with types. Okay, in a language without types, you've got to run the program to find out what value is in the variable to find out if it's a correct value or not. Yeah, because there is nothing about f that tells you what f is. You know, because you can do set f5, set f false, even more weirdly, set f randomly. Yeah, you can write that in Python, you can write that in JavaScript, you can really do this. And there are people who do really strange things like that. But that's one of the reasons why JavaScript and Python are poor choices of a programming language if you're writing really important code. Like you would never write airplane navigation systems in Python. You know, all the people who talk about how wonderful Python is, they have to admit that massive, massive, massive amounts of code the world needs can never be written in Python because of the lack of safety of it. You know, a Python program, you don't know if there's a problem until you run it. There's no way you can know if there's a problem until you run it. That's inherent in the language. There can be lurking in a program. You could have been running this program for 20 years and there could be a bug lurking in it. As simple as where at some point a function has an inappropriate value and you call that function and it crashes. Okay. C programs obviously can have bugs in them, but they don't have the kind of bug that Python can have. You can never have that K be an inappropriate function value. The compiler would never let K pick up an inappropriate function value, you know, because it's always keeping track that when you assign variables, they always are assigned from the same type to the same type, from the same type to the same type. So when you get down here, you know that K has the right type. Okay. Python programs, you don't know the type of a variable until you know what value's in it, and you don't know what value's in it until you run the program. Okay. In our language, we can do the following. If the variable name is the original definition of the function, then you can type check it. So what we're saying is that if you apply a name that's actually the original name used in the function definition, then it's safe to type check it. But that means it can't be a local variable like that one, because then you have no guarantee that f is really what, you know, where it came from. See, once that variable gets assigned some value, you lose track. See, once you assign something to a variable, you lose track of what value it has. But if you can go back to the original definition that's never been redefined, then you know what it is. Okay, so if you can go back to the original definition and it's never been redefined in between, then you know that f is that guy. So you know what its type is because you're going back to the original definition. Okay, but if there's any intermediate definition, then you just can't say anything. You know, once f gets reassigned, f is being reassigned to g. What's g? Well, now I have to run the whole program to find out what g is, because God knows g could have been assigned randomly. In fact, you can't ask what g is because of these things. This is a famous theorem. It's impossible at compile time to know what the value of k is, because the value is chosen randomly at runtime. Okay, so the compiler never knows the values of these variables. That's impossible at compile time. It isn't until runtime you know what function k is, but the compiler knows what type it is. The compiler keeps track of the types, and it makes sure that the types are always never changing. Okay, you can never know until runtime what value a variable has, because the values can be assigned randomly. But and in a language like Python, there's no way you can guarantee me that that function call is going to be legitimate. Absolutely impossible. You can never tell me, oh, I have 100% guarantee that when you call that function, it'll be okay. Because no matter what you think you can guarantee, I can make a random choice between two functions. I can, in some place in the program, set that variable f randomly. And then, That's legitimate Python. Unless you somehow prevent, unless you strip the random from the language, but then the language isn't going to be very useful then either. But if you have a random function in the language, then I can assign variables randomly. And if I can assign variables randomly, you cannot tell me if that function call is going to be legitimate or not, because I'll run my program and assign the variable random results. I could have Bob as an integer and Alice as a function. So I have like a 50-50 chance of that being a legitimate function call.
Would you have to then account for all the cases if you were trying to do that?
I'm not sure what you mean. Account for what cases?
So where your apply F is, would you have to do like conditionals before that so that if it is a certain thing, go into there, and if it's
No.
can't do that?
No. Look, we're here. What should this be? It better be a function of two arguments.
Right.
If it's anything but a function of two arguments, you crash.
So yeah, so my question is in between the random set and where you're checking there, can you do some conditional that will determine if it's that case, then it will go into there, and if it's whatever Alice is, then it will have a different.
But that's what apply does. No.
That's what applies doing itself. Okay.
Yeah, apply has to check like in our interpreter. Go back to our that's what our interpreter does. Look at evaluate. Look up, evaluate, apply. See, makes this runtime check. See, it makes these runtime checks. First, it checks that it's really calling a function. So the first thing apply does is apply needs to make sure that apply first has to say, is that a function value? That's there. Check that you're applying a function value. If you're not applying a function value, crash. So if you've got a Boolean value or an integer value, you crash. Okay. So first thing apply does is check that this guy really is a function. Then the next thing it does is check, does it have the right number of arguments? Okay. So then after it's checked that it really is a function, then it checks, does it have the right number of arguments? So it checks the degree of the function call with the degree of the lambda expression. Okay. So it's checking, but see, now it's at runtime. It knows what function's being called. So it's at runtime. So apply has figured out what function that's a name for. It's figured out what its value is. So it's either this function up here, it's either this one or this one. If it really is a function, it's got to be one of those two. But now it's got a pointer to there or a pointer to there, and it can count the degree here, or like this degree would agree with that one, but this degree would not agree with that one. So if this f is really this function, it'll crash. If this f is really this function, it'll run. But at runtime, I'll know that this one, was this random choice this one or this one? Okay, like here, if I wanted to, I could make this make more sense. So I have some variable h. Okay, h is either f or g. H is either f or g. Okay, so create a variable h, give it a dummy value of false, just because you have to give it some dummy value to begin with, then randomly set h to f or randomly set h to g. So when you get down here, that function calls either this function or that function. There's no way in this part at this point where I can tell you whether that function call is legitimate or not, because I got, say, a 50-50 chance of it being the correct function and a 50-50 chance of it being the incorrect function. But at runtime, when I get to here, it's already been given the value. So at runtime, this guy has a value. It's either this one or that one. So the evaluator can check, is it a function? Yes. Then does it have the right number of arguments? Yes or no? Okay. So the evaluator, the condition is right there. The evaluator checks that it's really a function and checks that it has the right number of arguments. Okay. Okay. So, but you'd like the compiler to know whether this is correct or not. Okay. The compiler in a legitimate language will never compile this. Why not? See, this won't compile. This should not compile. Can anybody see why?
Ambiguous?
No, it's not
No,
ambiguous.
not
It's very clear.
ambiguous.
If what's
well, because
wrong
one of
with
them's
it?
not going to work. If
Pardon me?
one of them won't work because it won't be the correct
Yeah. So
number
what
of
does the compiler notice about that line of code?
wrong number of arguments.
Well, better description.
Better description.
Every variable has to have a type. This variable can't have two types, right? So there's no way that this variable can be assigned F or G, because F and G have two different types. See, F has type 1 parameter, G has type 2 parameters. So F and G have different types. So a compiler would say the type of F is not the same as the type of G, so you can't have a single variable that can be assigned to F or G. So the compiler will reject that line of code. H has to have the type, H and F have to have the same type. H and G have to have the same type, but F and G have different types. So this code can't compile. So I can randomly choose between two functions. That's perfectly allowed in C, but they have to have the same type. So they would have to be functions of the same type. So that would be something like there's two different functions of the same type. Now this is legitimate. See, now this makes sense. H has type function of two variables. F has type function of two variables. G has type function of two variables. I don't know which function H is, but it's a function of two variables because it's one of these two, but they have the same type. So the compiler will say, that's fine now. Notice I didn't change the code down here. Syntactically, that's completely correct. Now go back to the way it was here. Okay. Now this code won't compile. Notice I didn't change this code. I changed it up here. I changed the type of F. Because I changed the type of F, now this code down here won't compile because now F and G have different types. So this is a legitimate line of code because now that line of code compiles. So that means that's a legitimate line of code. Now that line of code doesn't compile. Well, it's still a legitimate line of code, but it doesn't have the right types now. It's syntactically correct, but it's semantically incorrect now because it doesn't have the right meaning. The H, there's no uniform type here. F and G have different types, so there's no type for H that agrees with both F and G. Okay, so the types don't agree here. So it's syntactically correct either way, but it's semantically incorrect now, and it's semantically correct now. Okay, that's how subtle this is. But the compiler keeps track of types. The runtime, the interpreter keeps track of values. The compiler keeps track of types, or it should, if it's compiling a language like C or C++. If it's compiling Python, then it doesn't keep track of types. There are compilers for Python. You can compile Python. There's nothing to stop you from compiling it, but the compiler doesn't know about the types. And so even if you compile Python, it doesn't become very efficient because you still end up having to have runtime checks like this. Because even though you compile the Python code, you really have no idea what anything is pointing at until runtime. So you have to compile into the code runtime checks. Okay. So if this language were Python, if this was compiled, you could compile this and it would compile, But down here, built into here would be a compiled code that said, oh, let me check what type of function I have here. Is it a function of two variables? If it isn't, I crash the program. The runtime check is in the compiled code. So the compiler isn't doing you much good. That's why people usually don't compile Python code. The compiler doesn't help much because the compiler just has to spit out compiled runtime checks. They're a little bit faster than interpreted runtime checks, a little bit faster, but not much. This interpreted runtime check is not much slower than a compiled runtime check. The real problem is runtime checks. So if you compile a language like Python, it doesn't do you a whole lot of good. It does you a little bit of good, but not a lot of good because you still have to compile into your code runtime checks. There is a compiler for Python. It's this guy here. See, it uses a just-in-time compiler. It does a kind of compiling, and it ends up being faster than regular Python, but it's still way slower than it's actually quite a bit faster than regular Python, but it's still way slower than C or C++ or Java. Okay, it's still way too slow even compared. It's faster than regular Python, but it's way slower than C++ and Java. Regular Python is incredibly slow, sometimes like 100 times slower than C and C++ and Java. Python is actually a very slow language because of so many runtime checks. Okay, because of so many runtime checks. Okay, and the compiler, it's an important idea. The compiler doesn't help much. If you compiled this, you'd still have to say, you'd have to compile into this thing the runtime check. Is H is H a function of two parameters, or is H a function of something else? So that would have to still be a runtime check. If there's no types in the language and you compile the language, you just end up compiling the runtime checks into the code. They're compiled runtime checks instead of interpreted runtime checks. Okay. So types are now adding types to our, if we had another semester, that would be the next thing to do in our language 7 would be to give it types. Okay. That's actually kind of that's a little bit more challenging even than what you're doing with right now. You're doing analyzing. Okay. Because if you put types in the language, then you can use those types to analyze. You can do the analysis using the types. Okay, and that makes you can actually write a baby compiler for the language even. Like we couldn't write a baby compiler for our language because it's just too babyish. It wouldn't lend itself to being compiled. But if we put types in the language, then we could write a baby compiler for it. Okay, but that's actually opens up a lot. It's way harder than what we're doing now. It makes things quite a bit trickier. You would do things like instead of saying there, you'd say bool here. Or you would say int g. So instead of just saying var, you'd say bool function. You'd say things like just like in C and C++, you say bool h, int g. Here you'd have to say something like fun. You'd have to declare this guy as a function variable. You'd have to declare these as function variables, but then you have to declare them of the right type. So then you have to have a notation for the type of a function, which is tricky. C did a terrible job of that. It's actually up here in some of what we did in class the other day. I don't think we actually looked at it. Let me show you. Let me remember where I put it. See that? That's declaring a variable h that's a function. That's not declaring a function. That's declaring a variable that is a function. All this gobbledygook here is saying that h is a variable of type function that takes in an int and returns an int. It's horrible notation, but there's how I declare a local variable that's the name of some function. Okay. And it's very crazy notation because it's hard to come up with a good notation for function types. And C did a terrible job of it. So notice that the type, see, H is the variable. Its type is somewhat, look, some of its type information is over here, and some of its type information is over here. It's insane. H is a pointer to a function that takes in an int and returns an int. H is a pointer to a function that takes in an int and returns an int. Okay, that's how you declare a local variable that's a function name. Okay, so that you get really bad things like that in C. I think there's some other examples. No, that was the only one, I guess. This one here, that variable there. This was one of the big problems in the C language. It's still, I mean, this is one of the problems in the C language, is that it's got a very bad notation for function types. When you want to when you want to play this game of having a variable be a function, yeah, like here's the name of the function, then I want a local variable, like I want a local variable that's a name for that function. In C, you get this terrible notation for it. There's a local variable that is a function, but the C language knows that H is a function that takes in one parameter and returns an int. I have to tell C exactly what H is. So H can only be a name for functions that take in one int and return an int. I can't accidentally have H point at a function that takes in a double. The C language wouldn't let me do that. Yeah, I wouldn't be able to have H point at a function that takes in 3 parameters. Yeah, the compiler knows that H is something that points at a function that takes in 1 parameter and returns 1 parameter. So I'm guaranteed at runtime that H always points to the right kind of function. May have no idea what function it actually points at runtime, but I'm guaranteed that it's the right type of function. Okay, and in our language, and in Python and in JavaScript, you can never guarantee at runtime that a function is actually pointing at the right thing. In JavaScript and in Python, every time you call a function, there has to be some code that makes a check to make sure that the function you're calling is of the right type. Yeah, you have to check, does it have the right number of arguments? Does it return the right kind of thing? And that code slows you down. Every function call has to be checked at runtime to make sure that the actually you can get rid of the checks. You don't have to have them there. But if you don't have the runtime checks there, your program's going to crash anyway. Because if you call a function of 5 arguments and you only give it 2 arguments, the other 3 arguments are going to probably either have garbage values or be undefined, and the program is going to eventually crash for some reason. Okay, so you could get away with not having the runtime checks. Just go ahead and pretend that you're calling that function properly. But the question is, which is worse? The runtime check, which gives you an error message, function call with a illegitimate number of arguments, or a program that just blasts forward, eventually crashes, and you have no clue what went wrong. That's the alternative. A faster program that crashes and you have no clue what went wrong. versus a slower program that at runtime says, oh, I'm supposed to be calling a function with 2 arguments, but I'm actually pointing at a function with 3 arguments. There's something wrong here. Crash with an error message that at this point you made a function call that was illegitimate. At least then you know where the mistake was. The alternative is faster programs that crash with no clue what's wrong with them. And in the real world, you get both kinds of things. Some Python interpreters can be one way. If you want speed and you're pretty sure your programs are correct, you don't want the runtime checks. If you're worried about being able to recover from mistakes, if you're worried about being able to figure out what went wrong when a program crashes, then you pay the price and you leave in the runtime checks. And at least then you get an error message when something goes wrong, as opposed to the program just crashing and you have, if you call this function with 2 arguments, it's supposed to take 5 arguments. The other 3 arguments can get garbage values. That could make the function call do something weird, but that may not cause the program to crash until sometimes later when something that didn't get set properly ends up pointing at memory that's invalid, for example. So by the time the program actually does crash, it could crash very far from where the real problem was. That's nightmarish. That leads you to code that you can never debug. So almost nobody wants that. Okay, so almost, it's pretty much Python interpreters and JavaScript interpreters do the runtime checking, even though it slows them down. Though there are, you can strip the runtime checks out if you don't want them there. But then you're worried about crashes being completely mysterious, where you have almost no hope of figuring out what went wrong. Okay. So compiling is important. Compiling, not only does it give you faster code, compiling keeps track of the types, and that's what's so important. It's actually keeping track of the types that's way more important than even compile. The fact that you compile the machine code is less important than the fact that you keep track of the types. Keeping track of types is more important than generating machine code. Okay? Because JavaScript can generate machine code. They do generate machine code with their just-in-time compilers, but they have to generate machine code for the type, for the runtime. They have to generate machine code for these runtime checks too. Okay, so you end up having to, the compiler, the generating the machine code is not what a compiler is really doing for you that's so important. What a compiler is really doing for you is important is keeping track of types. But then the language has to have the types in them. The language has to have something that denotes the types. So you have to come up with a syntax for denoting the types. Okay. So the static analyzer starts getting us talking about these ideas. That's why the assignment's for you to write the static analyzer, because it's starting to bring up where you can think about what's really going on in a programming environment. Who is figuring out things? Who figures out where things are correct or not? Now we have three ways it can be done now. It can be done at runtime, okay? And it can be, well, actually two, it can be done at runtime, it can be done at analysis time without type information, or it can be done at compile time with type information. That's really what you want. You want this to be done with type information. So it can be done with or without type information before you run the program, or it can be done when you run the program. If you've got type information, you don't need to do any type checking at runtime. If you don't have type information, you can do some checking before you run the program, but not enough. Okay. So if you put type information in the language, then it's actually, it's great because you can do all the checking at compile time or analysis. Sometimes in a real compiler, some of the checking is done at analysis time. After you parsed it, before you compile it, you can do a check of some things. And that sometimes that's faster than waiting for the compiler to do the actual checking. So even in real languages, the analysis can be done like here before the compile, like this would be essentially before the compiling. What you're doing here, the static analysis runs before the compiler. So it could run after the parser, but before the compiler, and it can find some of the errors. Okay, and that can make life easier on the compiler. And then some of the errors would be left to the compiler. Okay, but in the world of real compilers, they kind of the compiler's got many stages: tokenizing, parsing, static analysis. Then there's various stages of static analysis where you catch more and more and more type errors. So usually the type errors are gathered in stages where you progressively get to be more, as each stage analyzes things, that each stage makes it a little bit easier to write the next stage. So you don't try to write an analyzer that catches every error. It's a little bit easier to write an analyzer that catches some errors. Then the next analyzer knows that those errors aren't there, so it can be a little bit easier to check for more subtle errors. Okay, so the compiler is essentially a sequence of static analyzers and then a code generator. Okay, so you're writing what would be like the first stage, the first simplest thing that a compiler would do. The simplest kind of error checking, but without type information. See, without the type information. So you can still do some checking. You see, you can still do some reasonable checking even without type information. Okay. And where it really becomes tricky is function names. Okay. So function names, you can check them only when they go back to the original function definition. If it's a local variable, forget it. You really don't know what function you're dealing with. Okay, so then you have to leave it up to the runtime system. Okay, but if that variable name has never been redeclared, so there's no redeclaring going on, and if that variable name is actually that one there, then you can say check that versus that. Okay, check the arguments versus the function, the declaration. Okay, so that's where the environment helps you. Remember, the environment knows how to distinguish between globally defined variables and locally defined variables, where it was locally defined variables. You want functions that are globally defined, then you can check them. Okay. Well, I've been going on. What about any other question about the homework? Because that's the hard part of the homework assignment is apply and fun. That's where the real work is. Okay. Any question about what I've been saying? Any question about how this works? Okay. The only advice I get, it's a tricky assignment. Just keep in mind, probably the best advice is think in terms of abstract syntax trees. When you're writing this code, have a picture of an abstract syntax tree maybe in front of you. Remember the program, like there's the abstract syntax tree. Keep that in mind. I mean, that's the way I do it. I actually keep these pictures. Like I remember them or actually will have them up in front of me. As I'm writing the code, I'm thinking, well, I'm down here in apply, and I have to think about over here's the lambda. Here's the apply branch. Here's the lambda branch. There's I'm checking if the degree of this is equal to the degree of this. Things like that. See, this has got one variable. This has got two. Things like that. Keep in mind the abstract syntax trees. So the code, if you run it through the demo version, it'll generate the pictures of the abstract syntax trees. To me, I mean, that's how I actually wrote all this stuff. I actually either on a piece of paper or one of these like this, I write the code thinking about what the abstract syntax tree looks like. Okay. And you might need a couple examples of abstract syntax trees. So, you can run this other one here. There's another abstract. See, there's a more complicated one, but there's a slightly more, think in terms of the, it's maybe kind of hard to think in terms of what this is doing. It might be easier to think in terms of what this picture looks like, because the static analyzer is walking this tree. Okay, this is the tree that the static analyzer is manipulating. Okay, so think in terms of the static analyzer being, down here at apply, trying to figure out, is this a legitimate apply or not? The abstract analyzer is sitting here trying to figure out if this is a legitimate function call or not. Is it legitimate to call that f with those arguments? Okay, and again, only if that f is that f over here. If that f is that f, you can compare them. But then there's an f here that's local that stops you from analyzing that f because of that f here. Okay. Now some of the, this f is not actually, you don't get it from the abstract syntax tree, you get it from the environment. So there's the environment floating around too. So it isn't only the abstract syntax tree that you have to keep in mind. You also have to keep in mind the environment. So the fact that this f is that f, it's the environment that tells you that, not the abstract syntax tree. So you kind of go back and forth. Think about the environment, think about the abstract syntax trees. But maybe, keep pictures of them in mind as you're manipulating things. Okay, so we'll quit there. Okay, and next week, same thing. If there's more questions about, after you work on the analyzer a little bit more, if there's more questions about the analyzer, we can look at those. Otherwise, we're going to look at, I have another language 9 that's kind of interesting. So we'll talk a little bit about the next language 9. So just to show you some more ideas, we can look at this language 9 that I wrote. But otherwise, if you have questions about the analyzer, we can go through more details of the analyzer. Okay. So if you have questions, send me email or come to office hours. But keep working on the analyzer. Okay. Any last second question? Okay. So have a nice weekend. See you on Monday. Bye-bye.